Hi, how are you all doing? I'm assuming you've never saw a video of mine, and I'll introduce myself again. Hi, my name is Igcse.science.notesz, and you'll find me on Instagram and Telegram, and here on YouTube as Igcse.science.notesz 8. Welcome back to the Physics A level playlist, where I'll be in this video explaining thermodynamics. Okay, it's only one paper or one page note, but we're not gonna only cover this part. We're gonna cover it like from flashcards, and we're gonna cover the definitions and other websites as well if we have time, etc. So, thermal properties of materials. Now we start with the internal energy. The internal energy of a body is equal to the sum of all of the kinetic energies and potential energies of all its particles. Again, sum of all of the kinetic energies and potential energies of all its particles is called internal energy. So kinetic energy and potential energy is internal energy. So basically internal energy is the kinetic energy and potential energy all together. So it's the internal energy of a body is the sum of all kinetic energy and potential energies of all its particles. Type. The kinetic and potential energies of a body are randomly distributed. The internal energy of a body is dependent on its state, since the state of a body is determined by the value of kinetic energies of particles. The internal energy of a system can be increased in two ways. There are two factors that increase the internal energy, either to do work or to increase the temperature. To do work on the system to transfer to it, for example, moving its particle or changing its speed. That increases the kinetic energy and so increases the internal energy. Second thing is that you increase the temperature of the system. Increasing the temperature of the system also increases the kinetic energy and so it increases the internal energy. As you know, the kinetic energy of particles is directly proportional to their temperature. Therefore, an increase in temperature means an increase in the average kinetic energy and so an increase in internal energy. These you could say that those are like some notes or stuff that we've already covered earlier in O level, but here in some more details that we said that kinetic and potential energies of the body are randomly distributed and that the internal energy of a body is dependent on its state, and since the state of a body is determined by the value of the kinetic energies of particles, so when we try to increase or decrease the internal energy, we try to decrease or increase the kinetic energy. Now we start with the A level part, the first law of thermodynamics. You know, first, what does the first law of thermodynamics describes? It describes the conservation of energy in a system where energy can be transferred through doing work or heating. First of all, what is the law of conservation of energy? Law of conservation of energy is that energy cannot be created nor destroyed, but transferred, right? So here, the first law of thermodynamics describes the conservation of energy in a system where energy can be transferred through doing work or heating. Through doing work or heating. Now, that is thermal heating dynamics. So, doing work or heating only. So, in this first law of thermodynamics. Also, although it can be like transferred many different ways, but here the first law of thermodynamics transferred through doing work or heating. It states that the increase in internal energy either by increasing temperature or increasing the work, so either increasing temperature or increasing the work, states that the increase in internal energy of a system is equal to the sum of the energy transferred to it through heating and work done on the system, and it's given by the following equation. Here the delta U basically represents the increase in internal energy. If the delta U is negative, then it is a decrease. If it's positive, then it's an increase. Number two, basically that the Q here is the energy transferred to the system through heating. Therefore, if Q is negative, energy is transferred away. Letter W is the work done on the system. Occurs when a gas is compressed. Therefore, if W is negative, work done by the system work is done by the system occurs when the gas expands. So basically, let me tell you something. Whatever. It's here the first law of thermodynamics describes that conservation of energy in a system where energy can be transferred either through work or through heating. And it states that the increase in internal energy of a system is equal to the sum. So when you increase in energy, it's equal to the sum. So there is a sum of equal to what? Equal to the sum of energy transferred energy away through heating and work done on the system. So either heating or work done. So we put energy transfer, heating, and energy work done. And we start breaking it down. Delta U, which is basically the internal energy, is equal to, here, delta U, which is basically internal energy, is equal to the sum of energy transferred to it through heating and through work done here. Okay, this is it. So the delta U is basically, as we said, the internal energy, which basically, if it's a positive number, then means it's an increase. If it's a negative number, it means it decrease. Number 2, the letter Q. It's basically the energy transfer to the system. Therefore, if to the system, it's positive. If it's away from the system, it's negative. The same for work done. It's on the system. So it occurs when a gas is compressed. Therefore, if it's positive, it's on. If it's negative, it's by. And here the diagram shows a system which does work, which is known by the fact that W is negative. You have Q in and W out. So minus W. Okay? Q in minus Q out equal Q whatever. Great. Now we're done with the notes itself, right? So we're going to the flashcards to memorize, to like refresh our memory. No, to first the definition, to make sure we understand the definitions, and then we go to the flashcards to finish. The only definition we have is internal energy, which is the sum of all the randomly distributed potential and kinetic energies of the particles that make up a substance. So the flashcards, let's get started, and the fun starts now. Okay. Describe the arrangement and energy of particles in a solid and liquid and the gas. Basically, we haven't covered this now, but we must know it. So as I said, we've refreshed the memory. Describe the arrangement and energy of particles, solid, liquid, and gas. In the solid, it's regular arrangement and vibrate about fixed positions. For the liquid, particles in close proximity, constantly moving past each other, forming transient bonds. Gas, particles spaced very far apart, free to move in all directions, negligible bonding. What is the internal energy of a system? Basically the sum of potential and kinetic energies of a system. Does every particle in the system have to possess the same ratio of potential and kinetic energy? No, the ratio of the respective potential kinetic energy components may be randomly distributed within a system. What is the general relationship between the temperature of a system and its internal energy? What is the there is a positive correlation between the average temperature and the sum of its internal energy due to the kinetic energy, as we've mentioned. Why is there a pause in temperature when a substance is being heated to temperature at which phase changes take place? That's because when melting or evaporation occurs, intermolecular bonds are broken. Energy is required to break bonds, latent heat of fusion, and is therefore absorbed in the process, rather than being invested in raising the substance's temperature. What is the specific latent heat of a substance? What is the specific latent heat of a substance? It's this is basically from another chapter, but also refreshing memories. Basically, the energy required to change the state of a unit mass of a substance whilst keeping the temperature constant. Why is the specific latent heat of vaporization? Basically, not to cover this now. At a given temperature, all particles in a material have all same kinetic energy. True or false? Wait. False, because as we said, it's randomly distributed. So most likely value. Right? Let's just not complete because I think it's waste of time. Not waste, but it's a very easy chapter. So let me go directly to a really good website that we're gonna basically finish our video in. Like, I mean, what I mean is, like, we're gonna finish today's class in, you know. There you go. Legal? Anyways. Here. Ouch. Okay. We are doing thermodynamics, which is basically chapter 16. Here we go. Let's just revise for the last time. Thermodynamics. An understanding of energy from the Igcse or equivalent is assumed, which is basically that we need to know that the energy, the law of conservation of energy is basically that energy can never be created or destroyed. It can only be transferred, and that the internal energy is the sum of both kinetic and potential energy. طيب. Internal energy of a substance, which is basically U as we've mentioned, is defined as the sum of random distribution of kinetic and potential energies within a system of molecules. The internal energy of an object is intrinsically related to its temperature. For example, when gas is heated up in a container, the gas molecules begin to move faster, increasing its kinetic energy. For solid objects, when you heat them up, the molecules begin to vibrate faster. Both solid and liquid objects' molecules are bound by intermolecular forces. However, ideal gas molecules are assumed to have no intermolecular forces. This implies that for an ideal gas, as the internal energy consists of only kinetic energy and no potential energy, thus the change in internal energy for an ideal gas can be written as this. Okay? This is another formula that we haven't covered earlier, because this is for ideal gas, which we've covered, I think, earlier in the ideal gas chapter. But this is the formula. Delta U 3 over 2K delta T. Okay. We can therefore say that the change in internal energy is directly proportional to the change in temperature. Okay? And then we have the first law of thermodynamics. So for a gas in a cylinder enclosed by a movable piston, the gas does work by exerting a pressure on the piston and pushing the piston outwards. And we need to recall and use the W equal P delta V for the work done. And the delta U is equal to Q plus W. Since the piston moves outward, the volume of gas changes at constant external pressure. Therefore, the gas does work on the piston. Thus, we can say that work done when a volume of gas changes at constant external pressure is W equals P delta V. When gas expands, V increases, work is done by the gas. When gas compresses, V decreases, work is done on the gas. And the first law of thermodynamics is based on the principle of conservation of energy. When energy is put into gas by heating it or doing work on it, its internal energy must increase. Increase in internal energy equal energy supplied by heating plus work done on the system. The first law of thermodynamics is equal to delta U equal Q plus W, where Q is the energy heat supplied to the system by heating and W is the work done on the system. As we said, if it's a positive value, it means that there is an increase in delta U, means that the internal energy increased and heat is added to the system and work done is done on the system. If it's negative value, then the internal energy decreases and the heat is taken away and the work is done by the system. Therefore, when gas expands and work is done by the gas, work done is negative. When gas is compressed, work done on the gas is positive. Thank you for watching this beautiful video. Have a nice, beautiful day. Thank you.